Linear elasticity. That's where we're starting. All right. So there's some calculus, and if anyone wants to talk about finite elements after, I can go into details, but there's some calculus that you essentially calculate a huge matrix of your stiffnesses at this point, how stiff is it in both directions. And if we were in a linear situation, we can just invert that matrix and solve for our displacements. Exactly. So now let's have some fun. Let's open up the deal.ii VirtualBox. Okay, so I'll say now if there are people that didn't read the pre-sheet for this workshop. So the easiest way to try out deal.ii is to download the deal.ii virtual machine. And so even if you have Windows or Macs or whatever, you don't want to install Linux by yourself, you can download this little software and it'll launch a virtual operating system on your computer with deal.ii installed in it, with stuff that you want to visualize deal.ii with already installed in it. Everything that you need to get started with deal.ii. So deal.ii. I had this open, but my laptop decided to restart right before the workshop. So. Okay, and let me zoom in a little bit so it's easier for you guys to see what I'm typing. Is that big enough? A little bit bigger, I think. Is that readable? Yeah. Yeah, okay, cool. Okay, so when you install deal.ii and you go in, you'll see that there's this folder called examples with like 85 different subdirectories. These are all example programs that you can run and read and learn how to do deal.ii, and they're all showing different capabilities of the code, solving different physics. I picked out a couple that we'll look at. So we go into step 8. It's here. Okay, let's go back to the slide for a second. I'll tell you what problem we're solving. Okay, so we're going to solve a problem where we have this square mesh, and we have a couple of concentrated forces in these regions. We have two forces pushing on the material in this direction, and one pushing up in the material in that direction. And we want to see if we can use a computer to solve what those displacements are going to be.
Are those forces only applied locally where those circles are?
Yeah, they're applied actually, if you know from finite elements what a quadrature point is. It's defined, you put a force at every quadrature point that's inside that circle. That's just how this particular problem is set up. Yeah. Okay. Okay, so if we look at like the main program in this C++ code, I'll just bring it up. Okay, so ignore this part for now, but basically what are the steps in a finite element, linear finite element problem? We're going to assemble our system, which is calculating that big matrix K that I talked about. We'll solve it, invert the matrix, and then output the results. What this loop is showing is this problem also is an example of one of the really good features in deal.ii, which is that it has the capability, if you have a problem where you want to refine your mesh only at places where the solution is like changing a lot and you need a lot of detail there are a lot of automated ways in deal.ii to refine your mesh to try to capture those details. And even though this problem, it doesn't really do anything, we'll show just kind of like how it does that. And what else did I want to show here? Oh yeah, and let's go to this assemble system step, and we'll see the code for how that bilinear form is integrated as well. So you're seeing the level of detail in deal.ii and how it really edifies your knowledge from taking finite element courses or studying it on your own. Oh. Down. All right, I guess we're scrolling. Oh, here it is. Okay, cool. I don't know why that search wasn't working for a second. So here's the money shot here. Yeah, so here you have this cell matrix. Deal 2 calls elements cells, but same thing. And you have this big loop that you're looping over all your cells, and you have those material quantities lambda and mu, and you're basically accumulating those contributions at every degree of freedom, every point in your mesh. So I wanted to show you guys that to see how deal 2 is so much like going from equations just to code. And now let's look at the results. And yeah, so when you're in the virtual box for deal 2, they have this software called Parity. You might have used it before, but this is a very common software for visualizing finite element solutions. And that's what we'll use today. Just go up here and open it. This solution was generated by the code. Oh, and Mahesh, if you're able to run it, let me know. I will also demonstrate how to run the code in a second. Here we go. So here you can see we're showing the x displacement, and as we expect, that x displacement is concentrated around the part that we applied the forces at. And the y displacement here is concentrated in the center. Let me show you guys what the mesh looks like. So we start off with this very regular mesh, and now I'll show you that cycle of refinement, what it's doing. It's trying to, you can see, even though I'm looking at the y displacements, it's also considering what's happening in the x displacements. It's refining the grid around where things are happening. And let's just look at the sequence. It looks like that. So yeah, you can get very, very dense meshes, even if your solution has like really high gradients. Deal 2 has really optimized ways to solve that. Okay, so now I skipped ahead. Let me show you actually how you run Deal 2 code. So John, when you got your CMake error, was that with the directories that we put on the GitHub?
Or it would have been, I mean, I was trying to, really what I was doing is I was trying to download from using Candy, like on my local machine.
Oh, okay.
And it didn't work.
Okay.
Honestly.
I'll talk to you. Yeah, I'll talk to you after some other time about that.
Yeah.
Okay, so Deal 2 programs are compiled using this CMake format. So the first command you need to run is CMake, and then dot just means run it at this directory. There's this file called CMake cache, and that just basically finds all the dependencies for the Deal 2 library for this problem that you want to solve. So we run that, and we run make. You can just run make, but I'll give you guys this little tip. If you type J, you can say how many cores you want to use, and that will help you compile your program a little bit faster. And this is a very quick, very small program, so it compiles right away. And now let's run it with 8 cores. So you do make run. This should just finish in less than a minute. Okay, yeah, so this is that refinement. It's telling you how many elements you have, how many degrees of freedom you have, and then how that increases as they try to refine the problem. So Mahesh, is it running for you? You have an error? Okay, yeah. No problem. I think it has one more cycle to go through. Last one's always the longest. Okay. So we don't need to go back and look at the results because we already looked at them ahead of time. So awesome. You guys can now go home and run deal 2. I told you the 3 commands that you need, right? That's it. But we'll look at 2 more examples, I guess. Okay, so here's the first example from Jean-Paul. This is a classic problem in finite element analysis called Cook membrane, and it's just this cantilever sort of beam, and then we're going to apply a traction force on it, just pushing it up, and we'll see actually what shape it gets into after running the program. So again, I'm not going to talk a lot about physics, but basically that K is now replaced by something called a Cauchy stress, and that is defined by this strain energy function, which has 2 parts, kind of how the material is like experiencing a pressure, like a uniform pressure, and then how it's dilating out from like a uniform shape. It has these 2 parts and some material properties. Really, I just want you to know that there are some material properties that you would tune in that, and I'm going to show you how in deal 2, if you want to like say you want to do a study changing this material property by small amounts, the way you do that is you make this parameter file, you parse that parameter file in deal 2, and then it's a C++ variable. So I'll just show you guys really briefly how that works. And the difference between this step and the linear elastic step is actually that this matrix now is a function of your displacements, which means you can't just invert it and find your displacements. You have to try to find the displacements that give you the right stress and the right displacements to balance the force. And so you need to pass this to some nonlinear solver that tries to find those right displacements. Really super. Yeah, if I tried to like teach finite elements from scratch here, it would be all night. So I tried to be kind of brief. Okay, so let's go to the Cook example. And here I want to show you guys parameter file. Okay, so on top here we have a parameter file, sort of like analog to an Abacus input file, not really. You can define anything here and it'll become an internal variable in your C++ code. But here they have like some options about how they're going to assemble that big matrix. The manual way is like more what we saw on the last program, but they also have this option to use automatic differentiation. You can say what order of approximation you want to use for your finite elements. And I think there's, here's saying like how many elements you want in your mesh. And then these are just solver stuff. And here's like the material properties. So that's one thing I wanted to highlight. You can have this file where you put in some properties that you want to study and vary either statistically or to do some design study. That's basically how you do it. You have this file that maybe you edit and you're automating in Python, however you want to do that. And then when you compile the code, it'll be an internal variable in your deal 2 program. So how is that done? Let's go to the relevant function here. Yeah. So if you look at this declare parameters function, you can see how it's parsed. You have a subsection, and you enter that subsection, and then you tell it, what string to look for in that subsection, and what data type you expect it to be. And that's how you parse the file. Yeah, the way to learn how to do stuff in deal2 is try to find a bunch of examples that have all the pieces that you want, and then try to put it together. So if you want to use deal2 to do something like I described, then you can look at this example and see how it's done. That's why I'm not like reading the whole code for you guys. Good thing about deal2 is it actually has amazing documentation. If you go to the deal2 website and look at the step 8 tutorial, there's probably like 2,000 words about it. So it's really great. And okay, now let's see how this program is run. So very similar to the last one, we assemble our system, or make that grid system setup that's assembling this huge matrix. And these two are sort of like preparing to output the results and define your time increments, because now we have this big outer loop. You should be able to see. Yeah. So while time current is less than time end, we'll step through, solve our nonlinear step. Take our displacements, add it to the mesh, and then output results. So I want to also run this code live for you guys to show you one more thing. It'll be really convenient when you start working with deal2 to write some simple bash scripts. So those commands that I just mentioned, I put them in a little bash script here. There you go. CMake, make, change. Oh, let's run it with 8 cores. So I'll save this. And then if you run the script, it'll do everything. So there it's doing the CMake, it's compiling the program, and now it's already running it. And okay, when you're doing a nonlinear problem, or this is using the built-in deal2 solver, you use another solver, have different outputs, but you can monitor your solution. It's showing you the residuals of residuals should be like for the force residual, and then also the displacement residual. And if your program doesn't converge, you'll see an error, and then above it you'll see like what the statistics of your problem were. So this will take 2 minutes to run. Maybe I'll pause here to field questions or comments. Yeah.
Is it very hard to define a domain that's not just the square grid? Or
yeah, I will. We can look on the deal2 website specifically about the tutorial that talks about those sort of things. And I did manage to, when I was playing around together, import a mesh from an external software too. So that is totally possible. And deal2 has also a lot of built-in functions for manipulating meshes as well. Like one I was looking at is, say you want to solve a 3D problem, but you just have a 2D mesh and then you need to extrude it. There's a function that will take just the mesh information, not even the geometry information, and just extrude it for you. Or you can merge meshes. You can actually this Cook problem started as a square mesh, and then they have a function where they transform it into this like parallel right thing. Okay. So yeah, all of that is possible, whether it's from an external program or you have something that can be like a bunch of little chunks of kind of like elementary geometric features. You can build that up in deal2. And I'll talk about that tutorial program right at the end as well. Okay, cool. So it was able to run. Now let's open ParaView and see what happened. Oh yeah, another thing I just want to highlight here for this example is they have this little printout of the total displacement of the vertical tip of the problem. So you can do whatever post-processing you want in deal2 in the C++ program there's gonna be a line that's like, okay, this node, extract what the displacement is at the last time step and print this out. So now you're seeing how things work. Maybe you have this parameter file, you're changing material properties, you optimize that for a bunch of runs, and then what's the metric you care about? You print that out too, you know? That's the good thing about deal 2, it's very automatable and flexible to however you want to do things. Okay, let's open up here. Okay, so here's our region, and I'll just turn on the edges so we can see the mesh as well. And I'll loop it so that it keeps going. We'll see how this thing changes. There you can see it's being pulled up. And we can maybe look at the displacements. X. Oh, whoops, I just rotate. Okay, now you see a little bit of magic. This 2D problem is actually a 3D problem. The way we constrained everything so it's not really doing anything in 3D. But anyway, okay. Giving it away. All right. So there you go. That's one. Now we've done a linear problem and a nonlinear problem. And are we finishing at 7?
Yes.
Okay, so
if you got a good.
yeah, so we'll just skip the third example. I'll just give a couple of wrapping up remarks. Close this up, just bring. Okay, so another problem I was going to show was this plate with a hole. The only other thing is that these material properties are like rate dependent. I was going to talk a little bit about that. Whatever. We did linear and nonlinear, that's enough. Some other useful tutorials that you may want to explore, and you can revisit all the tutorials I showed you on the deal2 website as well. It'll go into much more detail. Steps 3 to 5 are like heat transfer. That's kind of also like the simplest problem in finite element analysis, so it's a good place to start. Step 42 is a contact problem with an elastoplastic material. It's pretty interesting that you can do that. And then Jacob's question about external meshes and transforming meshes is step 49. So in light of time, I won't go there, but you can go and read it if you want to look into that. And finally, I'll just give you some advice on other places to learn deal 2. Like I said, those 85 tutorial programs are all like really well commented and explained on the website. So you can go there, just like keyword search whatever physics you're interested in, run the program, play around with it. There's also these lecture videos by Wolfgang Bangernath, who's the main developer of deal 2. And they're great. I mean, it's like a finite element course and learning deal 2 all in one. It's 50 lectures that are around like 25 minutes long each, but they're really good. I mean, you can just look at the ones that kind of focus on what you're trying to learn. And also just a shout out, there is a course by now previous faculty at University of Michigan, Krishna, and that is, but all the lectures are on YouTube. You can just go watch them. And then finally, we have, there is for deal 2 a Google group, and let's get verification. I wanted to actually show you guys this because I was just looking here yesterday, and there's going to be a deal 2 workshop in Colorado in August. So maybe you want to go to that. So it's worth it to see what people are talking about here. And if you get into some problem, you can post it there and people get back to you pretty quickly, actually. So it is a very like active user group and people are willing to teach you. Wolfgang is doing it all the time, man. He's crazy. He's awesome. He's answering questions. Well, we've almost hit our time marker. There's one last thing I was going to say, but I don't remember what it was. Any other questions? Oh, let me show you the external mesh that I imported. Yeah, just to prove to you that it works. Where did I call this? I called it M. So here I took one of those heat transfer problems. And this would be a good punchline. So this is some heat transfer problem that I defined on our Unich logo. And so it is possible to bring in external meshes. And I'll just go over time another minute just to show you guys what I was trying to do here. I was playing around with those adaptive mesh capabilities that I mentioned in deal.ii, and there is an option to do grid refinement in a way that tries to optimize both your gains and accuracy and how fast your next iteration this refinement will run. So I tried to run and see what happens. You can see it's trying to capture details around regions of interest. And I'll upload this to GitHub as well, so you guys can see what the steps are to bring in an external mesh as well. Thanks a lot for time and the attention. And if you want to talk about anything in more detail, you can always reach out to the club or to me. And my name's Tim Thompson, the way I think I said. But thank you.
Thank you, Tim.
No problem.
Tim, for an awesome workshop. Yeah, so that's pretty much it for our meeting. We have just a few announcements to go over now, but that shouldn't take too long, and then we'll be out of here.
Oh, yeah, I'm gonna try to make it this time.
Okay. Yeah, so just first announcement is I just want to remind everyone or let you know for the first time about our coffee hour program and just a few more details about it that we didn't specify last time. So every Tuesday we have this coffee hour where you can come and get free coffee at this place called M36 Roasters. It's on Central Campus. It's like somewhere in some direction from here. But yeah, there it is on the map where that little dot is. So you just Tuesday from 10 to 11 a.m. You come. It'll probably be me there. You can just come up to me and ask for coffee, and we'll buy it for you. And you can ask questions about the club if you want. So there's 2 levels to it. So make sure to look on both levels because we'll probably be in the basement because there's more space down there. But you can look out for a sign that looks like that. I'll have that on the table so you can know that it's me if you forget what I look like, or if it's not me there. But yeah, I think we're also gonna open it up to like I'm also thinking about opening up to like a Slack channel, like if you just want to like put your order in the Slack channel and come pick it up, that can work too. That's really our one announcement. But here's multiple resources we have. If you're interested in starting a club project, you can scan that QR code to figure out how to make a proposal for it. If you want to have your own workshop like Tim just made, you can put your workshop idea in with that QR code. If you want to visit our website, this is our